Feed water is heated in the chamber by mixing it with superheated steam at 20 degrees Celsius and 200 degrees Celsius and 1 megapascal. The goal is to determine the mass flow rate ratio. The feed water is the superheated vapor when the mixture exists as straight liquid at 1 megapascal. Solution step. Phase 1 you should be make assumption and properties is a steady flow state process, no change with the time, negligible kinetic and potential negligible and kinetic and potential energy gains, no work interaction or heat transfer, adiabatic mixing. Properties are taken from the steam tables, and relative and absolute values from the steam tables. Feed water T1 equal 5550 degrees Celsius. Compressed liquid approximated as straight liquid at 50 degrees Celsius. H1 equal HF at 50 degrees Celsius equal to 209.34 kilojoule per kilogram over kilogram. Superheated steam T2 equal 200 degrees Celsius. P2 equal 1 megapascal. H2 equal 2828.3 kilojoule over kilogram. Saturated liquid at 1 megapascal exit condition. H3 equal HF at 1 megapascal equal 762.51 kilojoule over kilogram. The mass balance. At the mass balance, for a steady state mixing chamber of the total mass flow rate entering equals the total mass flow rate leaving. M1 dot plus M2 dot equal M3, where M1 dot mass flow rate of the feed water, M2 mass flow rate of the superheated steam, M3 dot is the mass flow rate of the superheated liquid. Since M3 dot equal M1 dot plus M2 dot, the energy balance can be used next. Energy balance, the energy balance for the control volume is written as E dot in equal E dot out since the steady state process with no heat loss Q dot equal 0 and no work W dot equal 0. The equation simplifies as M1 dot multiplied by H plus M2 dot multiplied by H equal M3 dot multiplied by H. Substituting M3 equal M1 plus M2, M1 dot multiplied by H plus M2 dot multiplied by H2 equal M1 dot plus M2 dot all multiplied by H3. Rearranging them for mass flow rate ratio. To find the ratio Y of the feed water mass, flow rate M1 dot to the superheated steam mass flow rate M2 dot divided through by M2 dot Y H2 1 plus H2 equal Y plus 1 H3, where Y equal M1 dot over M2 dot. Rearrange for Y open bracket H1 minus H3 equal H3 minus H2. Solving for y equal H3 minus H2 over H1 minus H3. Substitute unknowns values using the initial values H1, H2, H3. We are given up. Substituted into the formula y equal H3 minus H2 over H1 minus H3. We get y equal negative 2.065.79 over 553.17, solving y equals 3.73. Final answer, the ratio of the mass flow rate is the feed water. Mass flow rate of the superheated steam is y equals 3.73. Interpretation. For every 1 kilogram superheated steam, add the mixing chamber 3.37 kg of feed water is the mixing to achieve the desired condition of the straight liquid at 1 megapascal. The negative sign cancelled out as expected since flow rate and initialize are positive in physical context. Problem statement: feed water at 500 degrees Celsius is heated to chamber by mixing with the superheated steam at 200 degrees Celsius and 1 megapascal. The goal to determine the mass flow rate ratio to a ratio of the feed water of the to the mass superheated vapor when the mixture exists as a saturated liquid at 1 megapascal. Solution steps. At the phase 1, we should be make assumption and properties. When the phase 1 of this assumption, steady state process, no change with time, negligible kinetic and potential energy change, no work interaction or heat transfer, adiabatic mixing. Properties are taken from the steam tables, relative ineptitude from values from the steam tables. Feed water T1 equal 50 degrees Celsius. Compressed liquid approximated as a saturated liquid at 50 degrees Celsius. H1 equal HF at 50 degrees Celsius equal 209.34 kilojoule over kilogram. A superheated steam T2 equal 200 degrees Celsius. P2 equal 1 megapascal. H2 equal 2828.3 kilojoule over kilogram. Saturated liquid at 1 megapascal exit condition as the final condition. H equal HF at 1 megapascal equals 762.51 kilojoule over kilogram. For the second step, and mass balance equations for the steady state mixing gamper. The total mass flow rate entering equals the total mass flow rate leaving. M1 dot plus M2 dot equal M3, where M1 dot is the mass flow rate of a feed water. M2 dot the mass flow rate of the superheated steam. M3 dot the mass flow rate of the saturated liquid, since M3 dot equal M1 plus M2. The energy balance can be used next. Step C is energy balance. The energy balance for the control volume is writing as E dot in equal E dot out, since it is a steady state process with no heat loss. Q dot equal 0 and no work. W dot equal 0. The equation provides you M1 dot multiplied by H1 plus M2 dot multiplied by H2 equal M3 dot multiplied by H3. Substituting M dot 3 equal M1 dot plus M2 dot, we get M1 dot multiplied by H2 plus multiplied by H1. Sorry, M1 dot multiplied by H1 plus M2 dot multiplied by H2 equal M1 dot plus M2 dot all multiplied by H3, because we are substituting M3 equal M1 dot plus M2. Rearranging for the mass flow rate ratio to find the ratio of Y of the feed water mass flow rate M1 dot to the superheated steam mass flow rate M2 dot divides rho by M2 dot Y H1 plus Y multiplied by H1 plus H2 equal Y plus 1 all multiplied by H3. Y equal M1 dot over M2 dot. Rearrange for Y multiplied by H2 by H1, sorry, Y multiplied by H1 minus H2 minus H3 equal H3 minus H2. Solving for Y equal H3 minus H2 over H1 minus H3. Substitute known values using the ineptitude values. H1 equal to 209.34 kilojoule over kilogram, to H2 equal to 828.3 kilojoule over kilogram, H3 equals 762.51 kilojoule over kilogram. Substituting into the formula, the main formula for Y equal H3 minus H3 minus H2 H1 or minus H3, Y equal negative 2.2065.79 over negative 553.17. Negative, we cancel the negative, cancel negative. Y equal 3.73. And the final answer, the ratio of the mass flow rate of the feed water to the mass flow rate of the superheated steam is Y equals 3.73. Interpretation for every 1 for every 1 kilogram of the superheated steam added to the mixing number 3.73 kilogram of the feed water is the mixing to achieve the desired condition of the saturated liquid at 1 megapascal. The negative sign cancelled out as accepted, since flow rates, and the NF3 are positive in the physical context. At the final, we said thank you for watching. We are Group 3, Salah Rahman and Muntasir.